So what's glycogen? Glucose polysaccharide, right? So how are they hooked up, the glucoses? Let's say, how are most of them connected? Glycosidic bonds. So we'll do a very simplistic diagram here. So what kind of glycosidic bond are we looking at here? What's the... Cool. And it just forms a big, long chain of glucoses, right? So every once in a while, one chain will branch with another chain. And what kind of linkage is the branches? Cool. Technically, that's review from last go around. So it doesn't mean you can't ask something about it now. So when would it be advantageous to make glycogen? When you have lots of glucose, by all means. This is your way of storing glucose. Where do you store this glycogen? Where does it get stored? Liver. Where else? In your muscles. So your muscles obviously store it because they may need it sometime soon if a lion starts chasing you. So why would your liver store it? Well, your liver is kind of that organ that's really responsible for keeping the blood glucose up for things like the brain and your red blood cells. So that's why the liver might store it. 2/3 of your glycogen's in your liver, the other third's spread out throughout your muscles. So, but it's, if you've got lots of glucose, then let's save some for a rainy day. That's essentially what we're doing here with glycogen. All right, here's your lovely pathway for making glycogen. Start with your glucose 6-phosphate. So at what point might we see glucose 6-phosphate? Say there was lots of glucose because we just ate a nice, fat, huge bowl of pasta. There's glucose just like flowing through my veins. So,
a lot of it after the insulin has already caused the glucose to come into the cell.
Cool. As soon as the glucose comes into the cells, maybe because of insulin uptake and stuff like that, it immediately gets phosphorylated by hexokinase. And so now I've got this glucose 6-phosphate. Cool. If I was going to do glycolysis, what would I do with this glucose 6-phosphate? Turn it into fructose 6-phosphate, but that's not what we're doing here. So in this case, to earmark it for glycogen, I have to first turn it into glucose 1-phosphate. Cool. From glucose 1-phosphate, it actually has to get activated, we say. So its activated form is this UDP glucose. UDP glucose. That is the activated form of glucose. So, and this requires UTP. So, and you pointed out earlier, what little minor product am I not keeping track of here? That 3rd phosphate. It's just inorganic phosphate floating around. So, but now this is activated, if you will, for making glycogen at this point. So, and that's your last step. So, in this case, we're going to take this UDP glucose. So, UTP. So what's the A in ATP? So remember your 4. Yeah. So just your other nucleotides, A, G, C, T, the U that you see in RNA. He's that guy. Cool. So and now that glucose is going to get transferred from the UDP to the end of glycogen with an alpha-1,4 linkage. And what's the enzyme that does this? Cool. Glycogen synthase. So I'll just say glucose N+1 has one glucose polymer with one new glucose on it, if you will. Question?
So the glycogen synthase, you have double arrows depending on
So, not in this case. In this case, I was trying to show that you're attaching this glucose to this glucose. Not a reversible step or anything. The steps were drawn out kind of right here. And this is where the glycogen synthase is acting. Cool, and now we're storing some glucose for a rainy day. And let's say it starts raining. Cool, so all of a sudden, low blood glucose for an extended period of time because there's, I'm starving, plane crash, high fat diet, something. I'm just not getting enough glucose in my diet for some reason. And so now it's time to use up my glycogen. So, and in using up my glycogen, I actually turn it back into glucose 1-phosphate. So in this case, this is glycogen phosphorylase. That does this. So if you notice, it cut a glucose off, if you will, and did what to it? It phosphorylated it. Oh, wait a minute. Didn't we have a name for things that enzymes that phosphorylate? Kinases. This is not a kinase, though, because usually kinases need to use up what? Need to hydrolyze what to do their phosphorylating? ATP or something analogous. This guy doesn't. He's not a kinase. He doesn't need ATP. This does not cost any energy whatsoever. So the glucose, when it's in the form of glycogen, we think of it as being already activated. When this phosphorylation happens from phosphorylase, no ATP is used up at all. No energy requirement for this step. Cool, and now that my glycogen's turned back into glucose 1-phosphate, I'm going to just head it back the other direction. So, for gluconeogenesis. Questions?
There's special enzyme that reverses the reaction of glucose 1-phosphate to glucose 6-phosphate.
So, that's a great question. I honestly don't know if there's a difference. If you notice, glucose 6-phosphate and glucose 1-phosphate are very similar energy-wise, so I would assume that's a reversible step. And I would assume it's just going to be the phosphoglucobutase that goes back, but I honestly don't know. So slides and book were silent on it. I'm just assuming it's reversible. Cool. One thing to note, I have left out a number of details along here that you're definitely going to want to study. So one of the sets of details we are going to talk about is this guy right here. So your glycogen phosphorylase, which was the guy we just talked about. So when you want to use up your glycogen, cool. So good times. Really, really good times. You guys remember this slide?
Yeah,
Exactly. So turns out glycogen phosphorylase has two different forms that differ in phosphorylation. So have a phosphorylated form, what we call glycogen phosphorylase A. We have a dephosphorylated form that is glycogen phosphorylase B. But then between A and B, those have two different forms. They have a tense and a relaxed state. You remember the terminology with tense and relaxed? What did that mean? So yeah, we kind of think of it as active and inactive, and it dealt with binding and stuff like that. So, but active and inactive, and notice the relaxed state, that's ready to do some stuff. It's the tense state that is so tense it can't do anything, so to speak. It's inactive. So however you want to think about it. So, but in this case, phosphorylation is just used to interconvert between the A and B forms, but then there are some allosteric effectors, so that then can turn tense to relaxed or relaxed to tense depending on the scenario. And that's what we're looking at. So notice phosphorylation, what kind of modification is that? Covalent, but allosterics usually involves non-covalent, just binding to a allosteric site and stuff like that. but binding in this case meaning just interactions, hydrogen bonding, dipole-dipole, electrostatics, all that kind of stuff, but not actual covalent bonds like we see in phosphorylation. So this is covalent. These guys are all allosteric and non-covalent. So in this case, if we look at this side here, does it make sense that glucose would turn the active state into the inactive state, and hence it's an inhibitor? Does that make sense? So what's glycogen phosphorylase do? So turning glycogen back into glucose 1-phosphate. And what's the goal? What's the goal of chewing up my glycogen, if you will? Create more glucose. Well, if I have lots of glucose, do I need to create more? No. Sweet. So that kind of makes sense. Sweet. Caffeine. So memorize it. And you can make it make a little sense if you want to. Notice I like to think of caffeine as having lots of energy. So personally, I could use a big fat something right about now, but along the same lines. One thing to note, so does this make sense? Sweet, no, yeah, I agree. So, but no, this doesn't make sense. This should be the other way around. And the one I post online, I'll switch it around. So, but it should be inhibited by ATP, glucose, 6-phosphate glucose, and caffeine. These are all evidences that energy or glucose itself is in well supply. And if I already have lots of glucose, and the whole job of glycogen phosphorylase is to chew up glycogen to make more glucose, well, if I already have lots of glucose, by all means, should I activate this? So no, I should be inhibiting it going the other way. So notice this is actually activated by AMP, but inhibited by the other 4 here. Unfortunately, I don't know which of these 2 forms is more active or less active. So I just do know that having these 2 different forms and 2 different phosphorylation levels does allow some fine tuning. So in the behavior of this particular enzyme. So if it only had 1 form, I've only got so much restriction on how active or inactive I can make this thing. But with 2 different forms governed by phosphorylation, I now have an extra level of government, if you will, over this enzyme to allow some fine tuning.